Good morning. Welcome to this session of Smart Manufacturing and Industry 4.0 Fueling Composite Materials Innovation. My name is Cynthia Hutchison. I'm with Automation Alley in Michigan. It's a pleasure to be your host for this session. That might mean I say the word manufacturing a lot because there's no way around it since we're talking about advanced manufacturing and composites, so you'll forgive me if I overuse that word. With the advanced manufacturing and process involved in composite manufacturing, it does make sense that suppliers are really focused on smart manufacturing methods to bring these materials and new industries to life. The need for smart manufacturing in this industry is critical to help ensure product quality and performance. Since composite manufacturing is a highly variable process compared to other traditional processes, it makes a difference that we have quality. We're looking for smart manufacturing to help maximize the efficiency and strengthen the supply chain. Many of the smart manufacturing principles that can be applied to composite manufacturing will ensure that automotive and other industries have the quality and performance levels they rely on from this industry. Things like additive manufacturing, incorporating advanced technologies such as sensors and artificial intelligence, and all the Industry 4.0 technologies like digital twin will make a difference in helping us reframe this industry. The biggest challenge facing the composite materials industry today is the ability to scale these technologies that are now available to meet the demand. For this session, we have people who help you talk about all of that. I'm pleased to welcome on stage three fantastic speakers. Ethan Eskowitz, founder and board member of Aris Composites. Marcus Kremers, CTO of Airborne. Hannah Dammers, research associate, ITA Group International Center for Sustainable Textiles. Welcome them on stage, and in a moment you'll hear from each of them. Each of the speakers will deliver a specific presentation, and at the end we will have a little bit of time to answer any questions from the audience. Now, the session today is sponsored by the Michigan Economic Development Corporation, MEDC, and I am pleased to announce my friend and colleague, Eric Schreffler, the VP of Development for MEDC, and he'll open the session. Hello, Eric. Welcome.
A culture of innovation that put the world on wheels and is now driving the next generation of transportation technologies. A legendary workforce that powers a statewide arsenal of innovation. A dynamic entrepreneurial ecosystem that captures the world's imagination and transforms concepts into creations. Vibrant communities and abundant natural resources that draw visitors from around the world, offering an unparalleled quality of life. For growth-minded companies looking for the right business environment for expansion or relocation, Pure Michigan means pure opportunity. A global supply chain located within 500 miles of 50% of the U.S. population with direct access to Canadian markets via 3 international border crossings. Access to the highest concentration of engineering talent in the U.S. and a skilled workforce among the top in the nation for advanced manufacturing. A statewide support network for startups, entrepreneurs, and small businesses, with a technology sector among the fastest growing in the country for annual tech job growth. The global epicenter of mobility innovation, ranking #1 nationally in automotive and mobility research and development. An international destination for foreign direct investment from across the globe. Historic downtowns and dynamic cities where people want to live. Combining a cost of living among the lowest in the country with a quality of life among the highest. When it's time to plan for what's next for your business, discover Michigan and discover pure opportunity.
Good morning, everybody. Cynthia, thank you for the kind welcome. On behalf of the Michigan Economic Development Corporation, I welcome you to today's session on the growing importance of smart manufacturing, also known as Industry 4.0. Michigan has manufacturing in its DNA. We might be best known for our global leadership in automotive production, but all across the state, from Detroit to Grand Rapids and up to the Sioux Locks, manufacturers big and small are making the things that drive the global economy. Life-saving medical devices, satellite electronics, professional office furniture, COVID-19 vaccines, tooling, and production and automation systems, to name just a few. However, in order to compete in the future, all manufacturers will need to understand, invest in, and deploy the smart manufacturing technologies available today, as well as the solutions of tomorrow that you all are inventing. In Michigan, we're working to support our small and medium-sized companies on their pathways to implementing Industry 4.0. We have enlisted partners within the state such as Automation Alley, a World Economic Forum Advanced Manufacturing Hub for North America, and a nonprofit Industry 4.0 Knowledge Center. And also the Michigan Manufacturing Technology Center, an extension of the U.S. Department of Commerce, with the aim of arming our companies with the knowledge and financial support required to embrace the smart manufacturing technologies necessary to drive their businesses into the future. In Michigan, industry, government, and academia are collaborating as never before to create the environment in which research, development, testing, implementation, and employee training can thrive. For those of you in the room today who have invested in Michigan, we thank you. For those who may be wondering about the opportunities that Michigan may afford your organization, please don't hesitate to find me or my colleagues, Bob and Vladko, who are sitting in the front row here, after this session. There's always room for more innovation partners, and Michigan is open for business. I hope you enjoyed the brief video outlining some of the things that make Michigan great, and I hope today's conversation will provide you with the insights and ideas on how we can all move forward together. We appreciate your time, and Cynthia, and I'll turn it over to you to start the session. Thank you very much.
Thank you. I think Eric really had to share the stage with that video because it was a great video. He did mention the World Economic Forum partnership with the Advanced Manufacturing Hub, and I would tell you my role at Automation Alley in Michigan, which is the Industry 4.0 Knowledge Center for the state, overlaps, and I am currently finishing a fellowship with the World Economic Forum where we help expand the Advanced Manufacturing Hub network to get all these great manufacturing intensive industries across the globe together. So it's been a wonderful opportunity to kind of see other places that are like Michigan around the world, and I'm sure many of you are from them. Next, I'm going to invite our first presentation to Ethan Eskowitz. He's founder and board member of RS Composites. Ethan, we're glad to have you with us today. He's going to deliver a presentation that I need to learn from on the problem of black aluminum, what we learned from it, and how is it different this time. So this presentation is going to explore what we've learned historically and anticipate the future of composites, how to partner with champions when the agents of change sometimes aren't change agents, and finally look at where the OEMs will find breakthrough composites in the future. Ethan, the floor is yours.
Thank you. So to manage expectations here, Industry 4.0, smart manufacturing, and how it's impacting our industry is a giant topic, far beyond what we can handle in the time that we have. I just started listing out here really some of the impacts, and we'll each on the panel speak to different areas that these topics are intersecting with the composites industry. But the bottom line is change, and the change takes these two forms. Incremental changes that we all see. Many of these themes have been impacting the composites industry for decades, and some of them promise to make significant changes in the time ahead. So while there's been a lot of incremental change, there are some disruptive things coming ahead. And that's really where I'm going to start our talks today, is focus a little bit more on some of the disruptive changes and new manufacturing methods. So black aluminum, I think probably there are folks in the room that could tell me all kinds of stories about this. This is a phenomenon that many people that have been in the composites industry have experienced for decades, where you will get a structural design from a customer that was designed for aluminum and really not taking advantage of the material that we have, so you end up with something with suboptimal performance. What this really illustrates, kind of from a academic business perspective, is this innovator's dilemma. And in this book by Clayton Christensen really became a bit of a landmark in corporate innovation, where sometimes what your customer wants you to do isn't the best thing for your business. And this phenomenon of black aluminum, when you take the customer's design that isn't as good as you could make, you don't want to do exactly what the customer says. You want to help them find the right thing to do. Also, kind of embedded in this experience that the composites industry had was this major shift, where in 1970, we were at almost 0% composites in a commercial aircraft, and now we're up to 80%. So we've had this incredible adoption that has happened. But when you go back in time, you might have been working on aluminum in 1970 for a fuselage, but that might have not been the most important thing, even if that's what your customer was looking at. But with some of the industries that are moving into the composites world, change happens much faster. So you look at, if you were working at BlackBerry on a keyboard when the iPhone came out, those keyboards and that brand went obsolete incredibly fast in some of the industries that are adopting composites. So we have to really think about these ideas of incremental versus disruptive innovation with these topics. Now, this is the adoption curve that many of us have seen before. The important thing about it is the curve doesn't always look like this. If you have a disruptive innovation, things can happen much faster. There's always been, many companies have counted on being the fast follower. The challenge sometimes being a fast follower is there are more and more significant rewards with being first to market in some of the industries as well. So this is another dynamic that we have to think about when we look at these three questions, a bit on the history of composites. So we went through these, we'll take them one at a time. The first is, what can we learn from the history? So, when we look at mechanical and structural designs, you have this series of steps that happen. Something is introduced, it needs to be validated and trained, and then the OEMs and the architects of the products need to digest that over time. The most important thing that comes through this cycle, you go through these iterations and you look at the places that you can impact your product, searching for more and more value, is you need to build that experience, build that training, build the competency within the supplier base. And you have the natural challenges associated with bringing your supply chain along, bringing qualifications along, and then the inertia of what was done before. And really what you get in terms of the bottom line is that change obviously takes time. However, the value creation that comes from coming up with a completely different architecture can be quite large if the disruption is quite large. So you're always balancing the question of how much value can we unlock, how much change can our supply chain, our customers bear on that way to a better future with the products that they're working on. So this naturally ties into the questions that we all face in making change in an organization. And this has really been broken down into individualism versus kind of cultural change. There are many ideas here that have been pursued, and we won't go into this in a lot of detail. But the important takeaway here is that it's that interplay of the champions and the individuals that are pioneering things and how they're bringing their organization along with them. But what we've seen is the most important elements that are necessary for these changes to be successful is whether the resources exist in the company and the objectives exist in the company to move to some new level or capture some market advantage through the innovation. So the perennial question always comes back to, so where's the big opportunity? And this discussion could be had in any one of these different industries where we could get into a lot of detail. However, in each one of those, it's really looking at the business case, and when you're looking at that business case, understanding how the culture, the ability of the organization to change works with the business case. And the important piece that I want to really end with on this topic of what we can learn from the past is that while things have changed very incrementally and slowly in many areas of the industry, what we see with the disruptors and some of the new industries that are adopting composites is things will happen much faster. So we have, incumbents are classically trying to take advantage of innovation, but many of the largest users of composites might not be here today. We'll have tens of thousands of products shipping, and most of our revenue as a company will actually come from folks that haven't been typically attendees of shows like this, that haven't been large users of composites. So really our pie is expanding significantly as these disruptors think about new ways to use our materials in these different industries. So we started with this question, and I had this kind of provocative this time. So what's the next time? So I'm just going to use our company as a quick case study and really to wrap up this talk. And I'm going to race through this. We would usually present a little bit of the background on our company, over the stretch of an hour. I'm going to try and pack it into about 3 minutes here. But the important thing is we went back, and Peter Thiel, who became a bit of a controversial but a bit of a thought leader in Silicon Valley, has this point about figuring out whether what you're doing is going to be valuable in the future, and figure out what you're best in the world at. And when we asked ourselves that question, it was the highest strength to weight or stiffness to weight parts in complex geometries. And we really came into the space, and 3D printing was popularizing these beautiful topology optimized shapes. And we said, why are 3D continuous fiber composite parts not looking like the structural ideals? So this is where we developed our solution, and it really goes down to this idea of having fibers aligned through complex structures, very much like the grain of a tree. And here you can see the traditionally machined composite laminate you can see on the bottom, and then the part that we replaced this part with, which has the aligned fiber within it. Now, what was required was developing a whole new way to do topology optimization and fiber alignment within the same part, and developing a software suite that enables customers to take advantage of design latitudes that have never existed before, in addition to taking advantage of many of the advances in smart manufacturing and Industry 4.0 with regard to the manufacturing systems that can produce incredibly high large quantities with very high degrees of repeatability at high cycle times. So essentially developing this new platform of design materials and manufacturing really related to many of the advances in these topics that we're talking about today. Here you see the simulation and the end parts. These are some brackets that we made for Northrop Grumman. And we're really one of the best recent examples of this. And a great just place to end on with regard to change was an announcement we just had with Airbus recently. So if you rewind almost a decade, our champion over there, Bastian, did this TED Talk about topology optimized structures and how they'll find their way into aerospace. And here, almost a decade later, we have this just beautiful topology optimized continuous fiber composite part And the impact with the weight savings and the lifetime fuel savings was really just staggering and very motivating for us as a company. But this was an incredible period of change, and we're not even talking about getting brackets on planes yet. We're talking about proof of concept here. So while many of the changes are long and protracted in our industry, some of the industries that will really take this up and move fast with it, these changes will happen much faster. The majority of our revenues as a company will come from the non-traditional composite companies in the years to come, and they are the ones that will really move things along quite quickly. And their needs are very different from the needs of the existing customer base, where end of life with the short life cycles of these products becomes increasingly important, as well as production capacity and locations. So while we have NPI in the U.S. and California, our first location was Taiwan, because mass production was required in Southeast Asia, where these products are typically produced. So. Let me wrap up at that point and just say that the impact of smart manufacturing and Industry 4.0 is really a growing pie for all of us in the composites industry, and I look forward to passing the microphone to my colleagues and hear a little bit more.
Thank you, Ethan, for. Yeah, that was very insightful, and I appreciate it. There are a whole lot of things I want to follow up with you, but we'll do it later, because we'll have a Q&A at the end of this, and you can ask Eric or Ethan any questions you have. So right now, next presentation is how to make composites easy, reliable, and flexible by going digital, which is going to tie very nicely into what we just heard. Marcus Kremer, CTO at Airborne.
Thank you. Actually, I liked the video about Michigan. And there was one shot of a windmill with tulips in front, so it reminded me of the Netherlands. So,
as it should.
So I'm from Airborne, and at Airborne we have 25-year experience of making and designing composite parts in many different industries. Typically, let's say advanced industries like aeronautics, space, oil and gas, but also some consumer goods. And always highly loaded structures in pre-preg, dry fiber or thermoplastics. What we currently do is we supply automated and digital systems to help customers becoming much more efficient. And our long-term vision is really to create technology that makes on-demand manufacturing possible. Currently we think many composite factories are quite static. It always takes a lot of time to set them up, and once they run for 25 years, for example, aerospace programs. But I think it's much more worthwhile to think about how to make the factory much more flexible or dynamic. So here are a couple of examples of products that we've made. We've developed many different technologies over the years, directly for customers, providing what they asked, but we have also developed new technologies that are let's say more disruptive. For example, there's a picture of a thermoplastic composite pipe on the bottom, and that's really a new technology that didn't exist. This is for offshore pipelines in deep sea. You have to think about 3-kilometer water depth, and what we wanted to make is a composite pipe that you can spool, and you have to imagine that 3-kilometer water depth is 300 bar external pressure trying to collapse the pipe. But still you want to have a pipe that you can spool, so it needs to be flexible. And that paradox we solved by using thermoplastic composites with a whole new manufacturing technology and also a whole new design philosophy, and created this product. So we make automated production systems, also very digitalized. I'll explain a little bit more later. And you see a lot of robots. We like robots because we want to make manufacturing flexible. So we focus on technology and products that are within reach of a robot, and that's literally within reach. So we don't focus on big wings of aircraft or wind turbine blades or other products. We focus more on medium-sized products and making that as efficient as possible. Because we are also still a manufacturing company, we are flexible in business offerings, so people can buy a machine or rent a machine, but we can also offer the service of manufacturing, where we run the systems for them in the startup, and once the volumes are higher, our customers then buy the machines and do it themselves. And that really helps to go through the innovation cycle, because it's always tempting to think about a fully automated factory, but customers find that difficult to do the investment now. So they rather go step by step. In some cases, they also need to see how the market develops. And with our offering, we can help them through that cycle. But having in mind always from the start that there is a solution to go to high-rate manufacturing. So from the start, we think about the right concept and then develop it with the customer. So how to think about digital manufacturing? For us, that's very important. So you have a machine to make a product. It needs two things: a machine program, a robot code to coordinate all the movements, and process settings. We're talking about composites, so we have to think about temperature, pressure, all these other variables that you have, how to deal with defects. Variations in the product, in the material are important factors. So we need these two things, and normally this takes a lot of time to set up. But we've created software to do this automatically and on the fly. It's automated programming. Some people call it zero programming. And it takes the input in a factory. It's design input, also material input, and operational input. In many cases, companies nest different products in one production batch. So we also have to think about the planning in a factory. And that's all taken into account through an import portal. And then we translate this into the right machine program and process settings. And it's really on the shop floor. So it's not an engineer doing this and checking it with a simulation. It's on the shop floor. The operator takes the input, pushes the button, and then let's say 1 minute later the machine can start running. And this makes production very flexible, and it makes it possible for the factory to follow the needs of the customer, but also follow, for example, disruptions in material supply, or there are problems downstream of a certain production process that can impact also the operation. At the back end, of course, we take the data out and create data insights for our customers, but we also use it to do what we call adaptive processing. And one example is, in many cases, composites need to be made in a clean room. So why do we have a clean room? Clean room is to keep the temperature and humidity constant. But in my mind, it's actually better to just go to any factory and not have a clean room, but to understand what the impact is actually of temperature and humidity, and with adaptive processing, feed that back into machines so that the system can just follow the variations. And the example I mentioned for these pipes, we apply this. You have to think about a factory of 100 meter long. We're making these 3-kilometer pipes in a continuous process. There's a lot of variation ongoing. The geometry of the pipe is changing over the length. We are at the sea harbor, so there's a lot of changes in temperature and humidity. And we didn't want to build a clean room. So we applied this adaptive processing approach to constantly adapt the settings of the process to avoid the costly infrastructure. And of course, we can also use this for predictive maintenance to understand what's happening to the machine and to correct the machine or repair it before we get problems. So this whole digital framework is for us very important. And I want to show you some examples how we did this. One slide about robotic programming. The traditional way of robotic programming is online programming, teaching, really on the shop floor. A more advanced option is offline programming or simulation, where the engineer does it so that the robot is not occupied by the programming time. But what we do is, let's say, the next level. We take also out the engineer and use automated programming to do this directly. So we're not only saving time on the shop floor, but we're also saving time for the engineers. So I want to talk a little bit about one specific technology, automated ply placement. So in composites, there are many material options. And a lot of people think about tape. And tape is great, but there are also a lot of other materials that are around here if you look at the show. Fabrics, of course, non-crimp fabrics, but also metal mesh. Sometimes you need to have an adhesive film or surface layer. If you have a sandwich, then there's a core material that you need to handle. But also recycled materials, they come in different formats. They can be chips or patches or fleece material. Yeah, and how to handle those. So what we've seen is that traditional solutions, they all use tape. Tape laying, fiber placement, and other technologies. And we wanted to do it different. Also to make real net-shaped laminates. What you see now in a lot of applications is it's near net shape. So you get forms like this, but still you need to trim it if you want to make a smooth hole or a smooth, let's say, circumference. So what we created is what we call automated ply placement. The principle is very simple. Execution is a bit more complex. We cut plies on the cutter. We use a robot to pick them and to place them and then stabilize it into a tailored blank. The nice thing is you can use this technology for dry fiber, thermoplastic and pre-preg, but also for a lot of different materials that are just shown. But if you think about handling composite plies, there are quite a lot of challenges. There are many different shapes. A typical factory uses many thousands different ply shapes, and it can be quite strange. It's not just a rectangular shape, it can be any shape. It's also flexible material, so you have to think about sagging and creating defects, so you have to be very careful about handling the materials. It needs to be high accuracy placement. And if you want to take a ply from, let's say, the nest, there are two challenges. One, pre-preg is quite sticky, so it tends to not separate so easily. And there can be the risk that you have not cut all the fibers. So to start with that last part, here you see how the system picks plies from the skeleton. And we have used advanced technologies with sensors that see if all the fibers are cut. And then if there's still a fiber uncut, the system will stop so that the operator can intervene. And there's also quite a lot of advanced technology in the end effector and also the vacuum belt underneath to make sure that we can gently peel off this the pre-preg ply from the rest of the skeleton. You don't see it in the movie because it's all inside the action, but if you really would look closely, then you would see that there's a lot of smart technology embedded in there. We also do adaptive ply handling, so with manual input, the operator can put the ply anywhere on the belt, and the robot will just adopt and pick the ply and just correct for any, let's say, placement or rotation that the operator has done. So we use that do that by using vision. We have a camera that sees the shape of the ply. It recognizes it, and then it goes into an algorithm that also combines it with a shape and material info, because one of the things we need to consider is sagging of the material, and that's shape and material dependent. So there's a real-life calculation going on to predict this, and then the algorithm finds the right way for the end effector to pick up the certain ply, and this is then the instruction that goes to the system. And this happens always on the fly. So this is really adaptive robotics, which is definitely not standard in the robotic world. And this is really the final system that you then get. The system doesn't need programming, as I said. It's really based on, in this case, DXF input. So if anything needs to be changed, you just need to change the input files. Material is being cut. Here during the pickup we check for any uncut fibers. What you see here is a vision system that checks the ply that's underneath the end effector for any defects. And it also has a real-life correction of the robot movement, because we want to achieve high accuracy. There's an on-the-fly correction of the robot movement based on what the vision system sees. So that's all running in the background. To minimize waste, we have also included the buffer. So if you want to minimize waste, the way to do it is to optimize the nesting, but it means that the order of plies coming from the belt is not the same order as what you needed, so you can put plies away. And once the ply is picked, here you see the vision table lighting up, taking a picture, and then placing it very accurate on the lamination table. Advantages, most of them I already explained. It's a very different approach than the traditional approach, I would say, with fire placement and tape laying. So now we have given freedom to the designer to use any material form that's out there. Can be tape or sheet. Sheet material is also possible. And we also make it possible to use wide rolls. And that means that you're not limited to just a slitted tape that's available on the market. Also, we can make 100% net shape parts, so it gives much more freedom to the designer with all the thickness variations that you need. This is a flexible platform. You just saw one system that's used for automotive, but we use the same technology, and I just put here two examples for aircraft, for example, very highly loaded frames for in a fuselage of an aircraft, but also for high volume battery structures for electric vehicles. And this system has a much more higher output of about 100,000 parts per year. Okay, thank you very much.
Thank you. That's okay, Anna. Thank you very much, Marcus. You know, the problem with having three really bright thought leaders in the industry all on the same stage is that we're going to run out of time for Q&A. So I'm going to ask all three of them to stay here, just kind of stay put when we're done, or mingle with the crowd and not leave this room, so you can do a Q&A. For those of you online, I'm sorry, the virtual access might be a little more limited, but we'll keep our time. I don't want to shortcut our last speaker. So our last speaker today is Hannah Demers, Research Associate of ITA Group on Center for Sustainable Textiles. I'm certainly very interested in hearing about that. So she would deliver a presentation today on Composite Factory of the Future and how to flexibly automate composite production through cobots. Thank you, Hannah.
Yeah, thank you very much for the kind introduction. So my name is Hannah Demers, and I'm a research associate at the ITA Institute. We are doing research on the whole textile process chain, so really from textile or from fiber production up to textile production, and then production of composite components. Today, I would like to welcome you to my presentation on Composite Factory of the Future, and in particular, I would like to talk to you about how to flexibly automate your production by the usage of cobots. I would like to start my presentation with showing you some pictures. Maybe some of them already look familiar to you. What we see here is the production of different composite parts. We have some that are rather big, others are quite small, and they also differ in the degree of complexity that they have. In fact, 40% of all composite parts are produced within manual processes, for example, vacuum infusion, pre-preg layup, or hand layup. And with that comes a problem to the industry, and I want to show you which problems arrive. So I've brought some quotes for you. I will just sum them up in short. When producing composite parts and also when introducing new employees to composite production, it's sometimes hard for composite producing companies to find really trained people, so they have to train them themselves. And here's the problem, that the training to do a proper composite part takes about 1.5 years to 2 years, depending on the part complexity and also the quality requirements. especially for safety critical parts, for example, in aviation or automotive production. There are also penalties coming up or follow-up costs in case of any error. And also, the companies have to rely on non-trained specialists, and we have a growing shortage of skilled workers. And what we have seen in the last 2 years within our pandemic, our COVID crisis, is that there is a growing need for smaller production cells and also flexible automation. So to sum that up, what is the problem with the manual process? Well, it's on the one hand slow, then also the quality is really depending on the worker's experience and also on his, let's say, mood. Is it on a Monday? Is it on a Friday? Is he having a good day or a bad day? And also we have this mentioned growing shortage of experts. One solution for this could be automating the process, but we have seen in the past that full automation has not always been successful. As for some companies, the initial cost is too high, you have to invest, you're limited in flexibility unless you're using the airborne approach, and also you have a limited part complexity. And that's where our ITA approach is coming in. We are looking at a semi-automated process. This is what we call the factory of the future, where robots, humans, and smart digital agents, for example, augmented reality, laser projection, or voice control, come together and work hand in hand. So we try to combine both worlds, the manual and the automated world, and then get all the benefits from both of them. We want to reduce errors, we want to increase reproducibility of the process, also increase efficiency, but remaining very, very flexible within the process. So as I already said, I want to focus today on cobots. Cobots, it's already in the name, these are collaborative robots. So what does that mean, human-robot collaboration? We see here on the left side a conventional production cell where human and robot are separated by a physical barrier, for example, a safety fence or cage. No physical contact is possible in between them, and the robot really runs at full speed and is doing his full automation job. On the right side, we see the more interactive parts. So here is the aim to really let human and robot work hand in hand. And when we're talking about cooperation or collaboration, it is always the case that they both have a joint workspace, they have a joint task to fulfill. And also, when talking about collaboration, physical contact is not only possible, but also required to finish the task. However, in these cases, the robot is always running at a reduced speed. Okay, so talking about collaborative robots, they are available at the market now for, I think, 6 to 7 years. What is different about them than industrial robots is that they have additional sensor technology and software to provide safety. They are quite easy to program, so you can, for example, teach them in by demonstrating something. And also, they are cheaper than conventional industrial robots. However, their payload and their reach is smaller or lower than those of industrial robots. Talking about safety, which is always important when doing human-robot interaction, there is a bunch of rules that can be followed, some ISOs, but you always have to keep in mind that a safe cobot does not automatically mean that your application is safe. For example, you cannot equip your cobot with a knife because it then can harm the human. So always keep in mind when developing tools for human-robot collaboration that edges have to be rounded, that materials have to be soft, for example, to not harm anyone. I have brought some examples of our lab with me today, what we have already tried. So one is using the cobot as a third hand. What we can see here is a cobot with a robot hand, like a little gripper. It can hold up one side of the textile so that it serves as a third hand for the human. This could also be applied to bigger parts by using bigger robots, for example. And the other approach we are looking at is the collaborative draping. In this case, we have 3D printed some tools to really stay flexible, to do a cheap tool. And what we are seeing here is, for example, a roller tool or a squeegee. We also have combined these two into one tool, which can be seen at our booth, so feel free to pass by. And what we do here is we split the draping task between human and robot so that the human is taking over the complex areas or complex geometries. So for example, double curvature surfaces or small diameters. And the robot is taking over the repetitive, easy areas of the mold. I also want to talk about programming a little bit. As I already mentioned, there are some plug-and-play solutions available, like Robot or Cobot Teach-In. There you really move the cobot from one point to another, and then the points are saved, and the cobot just follows the single points. This is quite nice. You can really teach in a whole process chain in maybe 30 minutes, depending on complexity, of course. But it's like a plug-and-play solution that is really easy applicable. And then what we are looking at our institute, this is quite a new approach and a project that has just started. It's called imitation learning. What we do here is we have experts demonstrating the process, so doing a draping task. We are taking videos by a depth camera and then deriving from these expert movements, robot movements. So what we do is we translate expert movements into robot movements, and the approach, it's an AI approach, it's called imitation learning. It's based on reinforcement learning. Okay, to sum that up, within our semi-automated approach, we aim at increasing efficiency and also effectiveness of the process. We want to improve quality. We are looking onto really easy programming, but always keep in mind, don't equip your cobot with a knife and rely on the safety restrictions. And also we are at the moment still looking for applications, so if you have something in mind, please pass by or contact me. And if you want to try the system yourself, we have brought different tools. We have brought our cobot, then feel free to visit our booth. We are right to the other Agora hall. Our booth number is Q91. And with this invitation, I have come to the end of my presentation. I'm looking forward to reshaping composite production with you. Thank you.
So I thank Hannah for her presentation. I also thank her for sticking within the timeline so that we have a few minutes left for Q&A. Would anybody, if you'd raise your hand, somebody will come to you with a microphone? I can't see if you raise your hand, so somebody up here has to tell us that. If we have any questions online, feel free to, yes, please.
So my question is to Ms. Hannah. So as you mentioned, with the human side, it takes 18 to 20 months to basically train them, develop them. So in order to develop an interaction between the human side and the robots, how much time does it take?
We did a user study at the beginning of this year, and we did have some non-qualified people there, and they were quite good at doing it. They were at least doing the same mistakes that qualified experts did.
Okay.
So it worked quite well, but we are also at the moment doing research on that topic because it's also interesting how to interact between human and robot, and we are always taking the human side into account.
Okay. Thank you.
You're welcome.
Thank you. Questions from the floor? I have one about scalability. We talked earlier about the fact that we're going to talk about scalability, and I'm going to think that this is either Ethan or Marcus is going to tackle scalability for me. Who would like to handle that?
He does big size. I do higher
Volume.
volume.
Well, it's I think the volume.
Quantity.
I'm asking a volume question. Yes. How rapidly do we scale this so that the industry is actually producing mass parts?
Well, the challenging thing with big parts is they typically involve architectures that take longer to change. So from a younger company perspective, we end up working on a lot of smaller products because they get to market faster and we need to generate revenue. We're very excited about big products, and as in the case we were talking about in my presentation, brackets for a commercial aircraft. We're very excited about that, but that is a very long-term investment that we won't be producing in nearly the quantity as the smaller parts for the consumer product space. But Marcus has lots of experience producing big parts, so let him address that.
Thank you.
Yeah, the size is important indeed, but I think the manufacturing technology is important to have that in mind from the start. So what you're doing is clearly a manufacturing technology that's already ready for high rate manufacturing. It's developed for it. But in composite, I think one of the nice things is composites, it's easy to start working with it. For metals, you need big machines and presses and how to make a prototype. And prototyping in composites is easy. You can do it in the workshop and you don't need high forces and just a simple tool in your own hands. But that's also the pitfall. Because it's so easy to make low-rate manufacturing, people start with it manually or with simple methods and processes and then are stuck if you want to go to high rate. So the challenge is to think about the high-rate manufacturing technology from the start and be ready for scalability. And that's not always the case. It's just how things go. And because composites are easy to prototype.
And I think one of the most, and I'll give an anecdotal, that one of the most exciting things that I see with composites is we've all talked about agility and resilience. Those have been our buzzwords for 2.5 years now since COVID. But I think that the agility and resilience they provide are something really magnificent for us in terms of opportunistic. And we just did a small pilot at Automation Alley in Michigan in partnership. We were connected through one of our advanced manufacturing hubs for the forum, the M Hub in Denmark. They asked us for a humanitarian effort for the Ukrainians, and they needed 10,000 units of something. We went to a large network of small manufacturers, and had them each produce their respective portions of it. It was a really interesting thing out of the gate. Halfway through, the Denmark folks called and said, we really don't need those clips anymore. Now we need a band. And we were able to just flip the design, put the new thing in, tell all the new manufacturers they had to start to make the new one. So that flexibility and agility gives me a vision into the future and how we're going to be able to really eventually large mass produce all kinds of things. So, any other questions? I've got to tell you, this has been a very informative day for me. I hope it has been for most of you. I'm looking forward to seeing all the booths. You all have booths here, right? And most of you have booths here. So feel free to connect with any one of us after if you have a one-on-one conversation with any of these speakers. I thank you for your time and look forward to having a wonderful day. I'm going to Q91. By the way, it was very nice to put that on the bottom there because I will remember Q91 and go there first. Thank you all.